Well, today we will talk about the third compact object, and that is black hole. We have already discussed a lot about white dwarf and neutron star, so let's start with black holes. Right. Now, in a way, you see these structures, astrophysical structures, they are quite interesting for several reasons. Now, the first one is that they are only, in a way you can say, one of the possible endpoints of stellar evolution. The possible endpoints of stellar evolution. What are the other two? Right? Do you remember? The other two are white dwarf and neutron star. Right? We have talked about this a lot. Now, not only that, you see, they are also powerhouses of the most luminous things in the universe. And what are they? What are these powerhouses? They are basically quasars and active galactic nuclei. Right? Now, the third point is very interesting. You see, the third point is that, in a way, you can say they are the simplest macroscopic objects in the universe. Why? Why do you say that they are simplest? The reason is that you need only the mass for a static black hole to understand its properties. For rotating and for charged black holes, you need another two parameters. So at most, you need only three parameters to understand the three types of black holes. So let us just now talk about the static black holes. And just you need a single parameter, mass. That's all. And you see, such simplicity we have discussed in our entire course. We have talked about so many phenomena, compact objects, right? Where have we seen such simplicity? Nowhere. But again, in spite of this simplicity, it needs a lot of mathematical rigor to just understand the phenomena near the black hole. Okay, we will look into it little bit details. Okay, so let's start then. So, what's the basic idea? How do we get a black hole? Now you see, if the core of a collapsing star, this is a collapsing star. Now suppose this is the core of it. Now if this core contains more than, say, 3 solar masses, then what will happen is that there will be no force which can stop the gravitational contraction. And you see, this object, it will not stop collapsing when it reaches the size of the white dwarf. Why? Because the degenerate electrons cannot support the weight. And later on, as it keeps on collapsing, again, it will not stop collapsing when it reaches the size of neutron star. Again, because degenerate neutrons cannot support the pressure. So this means that degenerate electrons can't support pressure, and also degenerate neutrons can't support pressure. So this means that this guy has no other option but to just go on, keep on contracting. Now, so there is no force which remains to stop the object to collapse. And where should it collapse? Collapse to zero radius. Now you see, as the object collapses, its density and the strength of the surface gravity increases. And if the object collapses to zero radius, so basically what we are looking into is collapse to zero radius. Right. So what will happen to the density and gravity? Because of collapsing to this, both density and gravity, they become infinite. Right. Now this is the very definition of singularity. Now, of course, in physical terms, it will be difficult to imagine an object of zero radius. Right. But you see, our physics is telling us that it will be doing so. So basically, this star having core with mass more than 3 stellar masses, it collapses to radius 0. And as a result, its density and gravity, surface gravity, right, keeps on increasing and increasing and increasing and becomes infinite. And this is basically a singularity. Now, what is a singularity? In a way, you can say that singularity is a place where the known laws of physics break down. You see, there is infinite energy density. The curvature becomes infinite, and so on and so forth. Now, let us consider a perfectly spherical black hole, which is basically the Schwarzschild black hole, right? Now you see, in this case, the singularity is a single point where the forces, the tidal forces, become infinite. However, you must also understand that this is not realistic. Not realistic as well. Why? Because if I add a mass, small mass, as it falls towards this black hole, Schwarzschild black hole, then if this goes and falls into the black hole, then it will not remain spherical black hole. Right? So it will no longer be perfectly spherical. Now you see, this is just one way of saying this. Okay, now when I was saying the surface gravity becomes infinite, then what does this mean? Anyway, let's talk about the gravity. So this means that everything, every object near it will not be able to escape the effect of gravity, not even photons. Right. Now, in this regard to singularity, let me just mention to you two very important concepts. So, related to singularity. I am not going to talk about the details. The first one is the singularity theorem. And what's that? Now, you see, let us talk about a trapped surface. What's a trapped surface? A trapped surface is a surface within which all light rays incoming and outgoing, they converge. So this is a definition of a trapped surface. Now this singularity theorem tells us that every trapped surface must contain a singularity, and this was proved by Roger Penrose. Okay, so this means that every black hole must also contain a singularity. So This means that every black hole must also contain singularity, since light rays will not escape from it. The next concept related to this is the cosmic censorship. Again, I am just saying you the statement in a way. Now basically what it tells is that every singularity is hidden behind an event horizon. Now of course I'll talk about this event horizon in a minute, but these are important concepts. You keep this in mind for the time being. Now regarding singularity, you might think that in a way this is impossible, and that when the laws of physics are better understood, they will show that basically this collapse actually halts at some subatomic radius and does not in itself goes to zero. So there should be a finite radius, although quite small. This is what you can think in a way, because going to zero makes life very hard to understand. But however, you have to understand that astronomically it makes little difference. You see, if the contracting core of the star becomes small enough, what happens is that, as I was just saying, the escape velocity in the region around it is becomes so large that effectively light will not escape. Right? Now let's just look into the details of it, basic details. Now let us consider an object of mass m which can escape from the gravitational potential well of mass capital M and radius capital R, and this will happen only if kinetic energy is greater than your potential energy. Right? Now we know this from basic physics. This means that half mv square is greater than gmm by r, and so this means that the velocity must be greater than some escape velocity, which is given by 2gm by r. Right? Now what's this value for our Earth? For Earth, this escape velocity, its value is 11.2 kilometer per second. Right? Now you see, we can increase this escape velocity here either by increasing the mass within a given radius or by decreasing the radius for a given mass. Okay? Now what happens inside a black hole? So you can say that this is say a black hole. Now what happens here is that if there is some light which tries to escape, then it will again get back. It cannot escape the gravitational field. So basically when v escape velocity is greater than c, then basically light will not be able to escape. Not even light can escape. And then we say that this enclosed region, this is basically our, you can say that this becomes a black hole in a way that you will not be able to see any light of it. Okay, not only that, in a way this tells us that we cannot receive any information of an object. So what is light? Light basically gives us information, right? Light gives us info about an object. Now, object. Now, what this means, this basic idea, this means that now we will not receive any information about this black hole or about the region near it. And such a region is, for these reasons, it is known as black hole. Okay. Now you see, if the core of an exploding star collapses into a black hole, the core would vanish without a trace. However, the boundary of the black hole is called an event horizon, because any event that takes place inside the horizon. So now we are going to define the region where beyond which we will not get any information, and that is basically, you can say, the boundary of black hole, and that is the event horizon. Remember, we came across it during the cosmic censorship, right? Event horizon. So this is the boundary of the black hole, and because any event that takes place inside this event horizon is invisible, so any event taking place inside event horizon, this one, is basically invisible to an outside observer. And so this event horizon is basically the boundary between the enclosed volume of space-time and the rest of the universe. And the radius of the event horizon, you see, the radius of the event horizon is basically known as Schwarzschild radius, and it is written like this for short, RS. Okay, Schwarzschild radius, or sometimes also written like R Schwarzschild. So basically the radius within which the object must shrink to become a black hole. Okay, now let us take a detour. So we have gone through all these ideas of core collapse, and then we discussed the boundary of a black hole. Now again, let us again start defining the black hole. Let us again start. So what's a black hole? Black hole is basically, now you can say, it's an object with an event horizon instead of a material surface. It doesn't have a material surface, but instead it has an event horizon. Okay, so any other object like a star, a white dwarf, a neutron star, they all have a gravitational radius, right? A material surface. They all have a material surface. So this means that they have a gravitational radius. Now for this object, black hole, it doesn't have this gravitational radius. How do you know that? Well, we will not be able to know that, because if we went there, we will go missing. Black hole will just take it away, eat us away, right? So basically you can say that it may have, we do not know it right now, it may have a gravitational radius, but we just saw, right, using basic ideas, that it goes to zero. So it may have a very small gravitational radius, but the event horizon's radius, which is the Schwarzschild radius, it is more than this gravitational radius. So this R Schwarzschild for the black hole is bigger than your gravitational radius. However, for these objects, you can just calculate the Schwarzschild radius, right? What's this? Is basically, you see, what is the Schwarzschild radius? You can see from here. You put the value of escape velocity equal to c, and you get the value of this r, and that's your Schwarzschild radius. So this is what I am saying. Basically, just let me put v escape is equal to c is equal to root over 2gm by r Schwarzschild, and this gives me basically r Schwarzschild is equal to 2gm by c square. Okay, now you see, for all these cases this gravitational radius is much bigger than your Schwarzschild radius. However, for this case it is the opposite, and you must remember this. Okay, so as I was saying, you see, events which occur inside this event horizon, they cannot be seen by an external observer, and this is the fundamental property of black holes which distinguishes it from the other objects out there. Now it is important to note that although there has been evidence for the existence of black hole in the universe, but the existence of the event horizon itself has not been demonstrated. Okay, fine. Okay, so let me again do a recapitulation. So basically, the critical surface where escape velocity is equal to the velocity of light is the event horizon, right? Now you see, below this surface no information can escape from the black hole, and so the event horizon is also sometimes used to describe the size of the black hole or the boundary of the black hole. Although remember that this is not a physical surface, but a mathematical surface, and also that it is used to describe the size of black hole. Right, now for a spherically symmetric black hole, this event horizon, so for spherically symmetric black hole, this event horizon is described by the Schwarzschild radius, and we just saw that the value of Schwarzschild radius is how much? 2gm by c square upon putting this from this, right? Now you see a detailed solution of the vacuum equations for general relativity. They also yield this precise same result. So keep this in mind. Okay, so you see, what's the basic idea? What can we say from this expression? So what we can say is that this Rs, or basically the size of the black hole, on what factors does it depend? You see, the other are just factors, 2g c square, they are constants. So it just depends on the mass of the collapsed object. So basically, a spherically symmetric object acts as a black hole only if its mass is concentrated in a radius less than its Schwarzschild radius, right? Let me write it down. So a spherically symmetric object acts as a black hole only if its mass is concentrated in a radius which is less than the Schwarzschild radius. Okay, now you see this Schwarzschild radius, which we have just written, we can write it like this, 2gm by c square. Now if we write it in terms of the solar mass, then the expression becomes like this. You can check this for yourself. You can take this as a homework as well. You can write like this, m by m solar, and this is in kilometers. So basically what it means, for a solar mass object, the Schwarzschild radius is of the order of 3 kilometers. Now you see, given that the speed of light should be constant, we might ask, how does light behaves when the escape velocity is equal to the speed of light? Now, to fully understand this question, what we need is we basically need the general relativity theory. Now, why? Because this theory describes the gravitational field around an object as a manifestation of the curved space-time, and we can gain some understanding of the effects of the curved space-time by looking at the metric. Now, which is important in defining distances. Basically, it helps us to define distances in space-time that are invariant or independent of the coordinate choice. Now, you see, around a non-rotating spherically symmetric black hole, the invariant infinitesimal distance is described by the Schwarzschild metric. Okay, so let me write down this Schwarzschild metric. You see, the space-time metric outside a spherical distribution of matter. I am not showing you the details. You can find it readily in any book on general relativity. A spherical distribution of matter is given by what is known as the Schwarzschild metric, and the structure of the metric is like this: T square is equal to 1 minus 2gm by r c square into c square dt square minus m by again r c square to the power minus 1 dr square and minus your r square regular terms theta and d phi square. Okay, now you see, when this 2gm by rc square is less than 1, then this becomes equal to the flat Minkowski metric, right? Now we have already talked about this when I was talking about the neutron star, and so in that case the GTR effects are negligible. And what's the flat Minkowski space-time metric? So it's basically your ds square is equal to c square dt square, this term basically here again, right, minus your dr square and minus this entire term r square into d theta square plus sine square, sorry, there will be a theta Sin square theta d phi square. Right? Okay. Now, let's start with the curvature of the space which resides in the radial term. Right. Now you see, so this is our Schwarzschild metric. Let me highlight this or underline this. So this is our Schwarzschild metric. Okay. Now you see the radial distance which is measured simultaneously, that means dt is equal to 0, between two nearby points on the same radial line. That means same radial line. What does this mean? It means d theta is equal to d phi is equal to 0 is the proper distance. This is known as proper distance. Right? Now, so we denote it in a different way. So it is like this. So this is our proper distance, and the value is dr divided by your 1 minus 2 gm by r into c square. Now I am doing this because we will need this concept. So thus you see the spatial distance. So what we see is that the spatial distance dl between 2 points on the same radial line is greater than the coordinate difference or coordinate distance dr. You can see from here this is less than 1, and so this means dl is greater than dr. Right. Now you have to understand that this metric here, it also incorporates time dilation. Let me show this how. Okay. Now you see, what's the time dilation? You see, this metric basically incorporates time dilation. And so what's the time dilation? Is basically the difference in the elapsed time which is measured by two observers. And what is the difference? The reason is can be either due to velocity differences relative to each other, or just by being differently situated relative to the gravitational field. So it also incorporates time dilation and also gravitational redshift. And what's the gravitational redshift? It is basically the process by which electromagnetic radiation originating from a source that is in a gravitational field is reduced in energy or redshifted when observed in a region at higher gravitational potential. Right. Now, suppose a clock is at rest. So, suppose if a clock is at rest at a radial coordinate r, then what's the proper time? That means the time between two events that occurred at the same location. right? Then this proper time it records is relative to the time dt that elapsed at an infinite distance by how much? So if this is the proper time, then we can write like this. Now note that here d tau is less than dt. So what does this mean? This means that the time passes more slowly closer to mass m, where the surrounding space-time becomes more curved. And this is basically what is known as gravitational time dilation. So you see our metric incorporates the time dilation. Now you see something interesting. So this we have shown here, this metric for a non-rotating scenario. Now again you see for this non-rotating star, when the radial coordinate of the star's surface has collapsed to the Schwarzschild radius, then what happens? All these two bracketed terms in this metric, they goes to 0. So let me write it. So for non-rotating star, the radial coordinate, when the star's surface radial coordinate, it collapses to this Rs is equal to 2gm by c square, then in the, which is basically the Schwarzschild radius, then in the Schwarzschild metric you see the bracketed terms, they go to 0, and the resulting behavior is very different. Let us discuss about that. So what happens after that? Now the proper time measured by a clock at r is equal to rs. So proper time measured by a clock, say at r is equal to rs, is how much? D tau equal to 0, right? See, from this expression it just become 1, so d tau is equal to 0. So what does this mean? This means that basically time has slowed to a complete stop as measured from our vantage point. At rest, and again at a great distance away from great distance away, right? Not close but quite far away. So what happens is that from our vantage point nothing ever happens at the Schwarzschild radius. So from our vantage point nothing ever happens at Schwarzschild radius, right? Okay, now let's talk about a different aspect. You see, the speed of light measured by an observer which is suspended above a collapsed star, what will it be? It will always be c. But for far away, we can determine that light is delayed as it moves through the curved space-time. Now the apparent speed of light, the rate at which the spatial coordinates of a photon changes, is called the coordinate speed of light. So let us put ds is equal to 0 for light in the metric, right? Then from there we can calculate the coordinate speed of a vertically, so we can calculate the coordinate speed of a vertically traveling photon. Now again, if we put d theta is equal to d phi equal to 0, then the coordinate speed of light in radial direction is given by how much? dr dt. So this is equal to just 1 minus rs by r. Right. Now what happens when r is much greater than rs? Then you see dr dt is of the order of c, as expected for flat space-time. Right. However, at r is equal to rs, what do we get? dr dt is equal to 0. What does this mean? This means light is frozen. Interesting, isn't it? Light is frozen in time at r is equal to the Schwarzschild radius. So this is interesting. Now let us not stop there. Let's see what more we can get. Let us use this expression. Okay, this one, the expression for the coordinate speed of light. Let us try to integrate this in the radial direction between, say, two arbitrary values r1 and r2. So integrating dr dt between r1 and r2, what we get is basically delta t is equal to, you see, r1 r2 dr divided by dr dt. We can write it like this, right? Or basically r1 by r2 again dr divided by c into 1 minus rs by r. Okay, now if you do the integration, you will see that we get this value. Okay, now it is important to remember that here we have assumed r1 is less than r2. Fine. Okay, now let's see what happens. Suppose let us insert, let r1 is equal to the Schwarzschild radius for the photon's destination. What do we get? If we put this, you see, we will immediately get that delta t becomes infinity. So if a distance observer, which is at r tending to infinity, it sends a photon to the black hole, then according to the distant observer, the photon takes infinite time to reach at the Schwarzschild radius surface, or the photon basically never reaches the surface. Now we can interpret this in terms of gravitational time dilation as the photon's coordinate velocity will slow down until it finally stops at the Schwarzschild radius in infinite future. Okay, so you see the spherical surface at r is equal to rs. It is very interesting. It basically acts as a barrier and prevents our receiving any information from within. And for this reason, a star that has collapsed down to within the Schwarzschild radius is called a black hole. as it is, and we say that it is enclosed by event horizon, which is the spherical surface at r is equal to rs. And as I have been already saying previously, this event horizon is just a mathematical surface and it may not coincide with any physical surface. Okay, now similar to a photon, any object falling towards the event horizon, what? It will suffer the same fate. Same thing will happen. So seen from outside, even the surface of the star that collapsed to form the event horizon would be frozen. And so you can say that the black hole is in a way a frozen star. So we have been talking about a non-rotating black hole, right? Okay, so non-rotating black hole. Now you see it has a very simple structure. Simple structure. Why? What does it has? At the center is singularity, right? Center is the singularity. That is a point of zero volume and infinite density where all of the black hole's mass is located. And also the space-time is infinitely curved at the singularity. And outside this singularity is basically the event horizon. So this non-rotating black hole has got such a simple structure. It has got just two features. One is event horizon defined by the Schwarzschild radius, another is the singularity. So you see, because of the event horizon, the singularity can never be observed. And so this is the hypothesis of law of cosmic censorship, which forbids that a naked singularity, which forbids basically naked singularity from appearing unclothed. That means without an associated event horizon. Now, since I have been talking about black hole, there are certain important concepts as well. One is a very important concept of no Hair theorem. And what's that? So basically this theorem tells us that all black hole solutions of Einstein's equations of gravitation and electromagnetism in general relativity, it can be completely characterized by only three externally observable classical parameters. So basically all black hole solutions can be characterized by only three externally observable classical parameters. And what are they? The three of them are mass, electric charge, and angular momentum. Okay. Now you see all other information, for which basically the hair is a sort of metaphor about the matter which formed a black hole or is falling into it, disappears within the black hole's event horizon and is therefore permanently inaccessible to the external observers. And so we can say that the black holes have no hair. So we have been talking about this non-rotating static black hole, and this is also sometimes called as Schwarzschild black hole. So this is a static black hole, also known as Schwarzschild black hole. You see, here it is only characterized by the mass m, since it does not have no electric charge and no angular momentum, only mass. So basically, as I have been saying, this is just characterized by this: a singularity at center, a mass m, and a Schwarzschild radius. That's all is needed to characterize this Schwarzschild black hole.